Welcome to our deep dive into hydrogen electrolyzer technologies. We'll compare primarily three uh, electrolyzers: alkaline, PEM, and SOEC electrolyzer. We'll compare to find the best fit for producing almost 10 ton to 16 ton of green hydrogen daily, and this will be powered by solar energy. So we can say that this is totally in a renewable route. This is critical for cutting CO2 emission in steel making. So let's get started. Now question arises that why does choosing the right electrolyzer matter? Because this is not a matter of a 1 day or 10 days. It is a very long term planning. So electrolyzer, as we know, it split water into clean hydrogen and oxygen, powering our goal to decarbonize, which is a very long term goal. And the right technology selection really impact huge on cost, efficiency, and scalability. So all these three factors going to contribute in a huge way, especially when paired with a solar power. So let's explore the option to ensure we meet now carbon goal efficiently. And in order to this efficiency agenda is very important. So now let us meet the three main electrolyzer technologies: alkaline proton exchange membranes, that is PEM, and solid oxide electrolyzer cells, that is SOEC. Each has unique strength for producing hydrogen, and after knowing these one by one, we will try to see in the next slide. We'll break down how they stack up for our daily target. Considering and all these electrolyzer we will consider in terms of solar integration and industrial need primarily. So let's switch over to our next slide, which is full of information. And as you can see that it is nicely break down into alkaline electrolyzers, and one by one we will share. Alkaline electrolyzers are the oldest, cheapest, and most durable, ideal for steady industrial hydrogen demand. PEM electrolyzers are compact and flexible, perfect for solar power variability. So always solar powers variability attached with this sort of electrolyzer. SOEC is used especially on high temperature steam for top efficiency, but expensive and still in development. For our system, we need to balance cost, flexibility, and longevity, as we have mentioned earlier also. Let's look at the next slide. Here, as we can see, a detailed comparison is there. Alkaline electrolyzer offer 63 to 70% efficiency, low cost, and 500 to $1,400 per kilowatt, and up to 90,000 hours of stack life. PIMS at 56 to 60% efficiency are pricier but excel in flexibility, ideal for solar integration. SOEC lead with 74 to 81% efficiency but have high costs and shorter, that is 10 to 30,000 hours stack life. For our setup, these metrics guide our choices. So let's go to the next slide. Here, especially our focus in on alkaline electrolyzer. Alkaline electrolyzer are the workhorse of hydrogen production. They are the most mature with the lowest cost. So maturity, cost are the highlights, and lowest cost, which equals to 500 to $1,400 per kilowatt, and can last up to 90,000 hours are the highlights. For our demand, they are a strong contender. However, their slower response to power changes, that is most important, slower response to power changes makes them less ideal for solar fluctuations. So let's see how PEM compares next. Now, as you can see, the PEM electrolyzer shine in flexibility. Their flexibility is wide, handling with 0 to 160% load changes. So a wide range of variability is there, perfect for pairing with our solar plant. So that's the best suited through the renewable energy integration. They are compact with a footprint half that of alkaline, but cost more, 1100 to $1,800 per kilowatt, with a 30 to 90,000 hours stack life. PEM's responsiveness to solar power makes it a top choice. And now, when we are talking about everything green form, then we must have to focus on renewable, and this electrolyzer becomes a highlight. Now, coming to SOEC, which operate at high temperature, 650 to 1000 degrees Celsius is its highlight, achieving 74 to 81% efficiency. They are great for future projects with waste heat like steel making, but their high cost, and this cost really matter, that is 2800 to $5,600 per kilowatt, and short, that is 10 to 30,000 hours stack life makes them less practical setup. But these are the future, but they are the future. It's not a it's maybe a new solution, but in future really it is going to have a huge impact. So which electrolyzer should we pick up for our blast furnaces? Alkaline is the best for a steady, low cost hydrogen production for industrial loads like our blast furnaces. PEM suits solar powered setups, handling power fluctuations for our 16,000 to 18,000 kilograms hydrogen per day target. SOEC is ideal, but we have high temperature waste heat and a long term vision. So let's summarize the decision criteria next. And regarding these, we can see the very clear conclusion, and we can say that we have to choose alkaline if cost and durability are priorities. So cost and durability, if priority is there, then alkaline is supposed to be the best, and it support our agenda. Now we have to go with the PEM if we prioritize solar integration, as its flexibility matches our solar plant's variability. As far SOEC is concerned, SOEC is a future option. If we can leverage waste heat for efficiency, let's compare them one last time. So finally, in a simple comparison, we can see that all the three, alkaline, PEM and SOEC, here together compared, and we can say these in final comparison, Alkaline offers good efficiency, low cost, and high durability, but needs more space. PEM provides moderate efficiency, excellent flexibility for solar, and compact footprint. And as far SOEC is concerned, it has a top efficiency but high cost, low durability. Hence, for our blast furnaces of having 16 tons short of requirement daily as far hydrogen is concerned, and to think of solar integration, then PEM strikes the best balance. Thanks.